Hello, so today we have a Python workshop and we will do an introduction to GIM and stable baseline for reinforcement learning in Python. So both the GIM and stable baseline are Python libraries. So I will first go over GIM, then I will introduce stable baseline, and together we will try to do a benchmark of RL, so reinforcement learning algorithms on simple environments. And we will also try to create our own environment, which can be maybe useful for research purposes. So I will start. So I have posted the link of a collab on which you can find some of the functions that I will use in this workshop. And if you want to do, well, if you want to also follow along, which is a good idea, I have put here, I'm sorry, my slide has disappeared. So I will put it in the discussion also. So I have just a quick list of libraries that I needed. So you need to have to do, oh, sorry, I don't know why it disappeared, but I will put it quickly. I'm sorry.
Have you tried the space key to go from one slide to another?
Yes, but I think it's because no, I think I know what happened because I think I put my phone on my keyboard and it's just on the X pouch. I think that's what happened. Okay, so just a few seconds. Put it back in the discussion. So you also have it on the collab. Okay, so there's a list of libraries that are needed if you want to follow along. Okay, so let's go. So I will start by we will start by looking at GIM. So GIM is a toolkit for developing and comparing reinforcement learning algorithms. So it was developed and has been supported by OpenAI since 2016. So it's completely open source, so you can go on GitHub and contribute. So I just put the link here. So the idea of GIM is actually to provide a standardized API for environments for reinforcement learning control tasks. So you have a simple learning tab that can be implemented as environments. So I will explain this a little bit in detail just after. And with GIM, you will have a standardized set of classes and methods that you can use to train, to interact with different environments and train different algorithms and realize different benchmarks. So the list of all environments are on this link here. So if I can just to show a little bit the diversity of available environments. Okay, so you have classic control tasks, for example, the CartPole or the motion cap problem, which are really popular and used to benchmark different types of control and learning algorithms in the literature. And you also have environment based on physics simulators, like Monroc, for example, where you have to train different animals or well, robots, humanoids or animaloids, I don't know if it exists. So you can train them to walk. So by the way, Monroc was bought by DeepMind, and now it's completely free too. So you can have a free license to play with it, which wasn't the case. Yes, exactly. Because before what happens? Because before you had to be a student, but now it's completely free. And so.
I like the name.
Yeah. Okay, and so you also have the famous Atari games, which are, I think, the one on which we had the first huge progress on deep reinforcement learning. I think it was with the deep learning algorithm that we will use later. And so you have all the whole games of all the games used in Atari, and I think in the deep learning paper, they actually just took a screenshot of the games, and just with a conventional neural network, they managed to learn how to play the different games. So you have a huge variety of environments, and all of them are completely standardized with the same API and the same methods. So we will see which one. Just a quick reminder about reinforcement learning. So in reinforcement learning, the idea that you have an agent that interacts with an environment, and that and the agent will learn an optimal policy, which is basically a sequence of action to maximize a signal, which is called the reward. So at each step, the agent will take an action, will send it to the environment, and the environment will return a reward. So the reward will basically guide the agent. That's the only signal that the agent will access to guide its learning toward an optimal policy. And the agent so will learn a policy based uniquely on the state, which is a sort of summary statistic of the situation in the environment. And just by looking at the state, it will return an action. So you don't necessarily make the hypothesis that the agent can fully observe the state. So in our case, we will continue with this assumption because it doesn't change much thing. It doesn't change a lot of things for the implementation in terms of coding. But you can also encounter environments and encounter situations, where the agent only observes partially the states, and so we will use this observation of the agent. We'll call it observation, whether it corresponds fully to the actual state or only to a past observation of it. And so the goal, so I don't know if, okay, so maybe I was a bit optimistic about the size of the slide. So usually you will have, I'm sorry, but you will have
Si tu as une souris, contrôle molette.
J'ai plus de place pour le prendre. C'est vrai que j'ai empiré le.
Ah, là, tu as fait un truc. Dans l'autre sens. Dans l'autre sens, la même chose dans l'autre sens.
Ouais, je sais pas. Ok, so bon.
Parce que si tu fais ça sur ton touchpad, si tu zoomes, ce sera un zoom logique.
Ok.
C'est un zoom dans ton navigateur.
Si tu vas dans...
Oui, ce sera du coup un zoom.
Non, mais tu ne les vois pas par rapport au scaling des slides.
Okay, so I will do a quick little something.
Ça fait ça zoome dans une zone précise.
Ah, d'accord.
Okay, so quickly we will go back here. So you will have, so usually you have what we call the discount factor, which is a gamma here, which will discount future rewards, so reward that you will have later in your trajectory in the environment will be worth less than the one that you can gain immediately. And your goal will be to maximize discounted, the sum of discounted rewards. Okay, so I'm going back to my slides, hopefully. Okay. So in GIM, this is represented by this set of 5 methods, of which really the first 2 are basically the most important. You can do pretty much everything you need to with the first 2 methods. So your environment, so I should maybe just take the opportunity here just to say, so GIM basically really focus on implementing these parts of the system. So Jim only cares about the environment. It's completely agnostic about the type of policy or agent that you're using to choose the action. For all he knows, maybe you're simply picking action at random. So Jim only implements a class that will, yes, that can take an action and returns a reward under state. So how it does it is by having these two methods. So you have a method set that will take an action and return the observation, the reward to guide the learning. Boolean dawn, which is just an indicator of whether the episode, whether your trajectory in the environment should stop right now or not. So for example, if you have, let's say, a grid where you have a starting point and a goal, as soon as your agent reaches the goal, it is what we call an absorbing state. So the episode is now done because the game is over, you have succeeded. You can also fail. So for example, if you have the same grid, but you have maybe a case where you have a burning fire, and if you win that case while you die, well, the agent dies. So in that case, well, you will also receive the Boolean dawn is false because you simply have failed and the episode is over. So you have the reset method, which will initialize and reinitialize the environment and return your first observation. And so basically the two most important methods. Then you have the render, which will just give you an image of your environment. So this can be useful, for example, to record a video if you want to have an idea more qualitatively of the type of policy that your agent is following. And so then you have a close method in case you're dealing with an environment that needs to maybe open a file or read something. So you can close it in that method. And then you have a seed, which is eaten here, but the seed obviously will allow you to set up your environment from reproducible results. So in particular, in your action space, we'll see that you can sample the action space. And so this allows you to always sample the same action at the beginning. Okay, so I will show you an example on a really classic control class, which is the CartPole. So okay, so you have this, so you won't fully see it, but you have a cart and you have a pole. I think you know it. Yeah. So and so the pole. Well, so the cart is can move left and right along a track, and your goal is to make sure that the pole stays straight. Okay, so I think I have the explanation here. Yeah, so you have your so the pendulum starts upright, and you try to prevent it from falling over. And so every time the pole is upright, you will receive a reward of +1. And the episode will end when it's falling. So you can look a bit closer at the way it's implemented in Jim. So we'll have environment, and so we'll have your environment class, and it will be associated to an action space and an observation space, so which are attributes of your CartPole and environment class. And so the action will be an NumPy array of shape 1, and you only have two actions, 0 and 1 for left and right. And your observation will have an array of shape 4 because you will have the cat position and velocity and the angle, etc. Okay, so how will we act in this environment? How will we interact with it? So, so it's pretty simple. So all the environments that are already registered and that James comes with are associated to an ID. So for example, the CartPole is CartPole V1. So you simply have to choose the ID, and you do g.make, and you have your environment. So now we have an example. So I don't know if maybe you can do it too. And you have the reset method, which gives me my first observation here. So again, and so I have here my observation of shape 4. So that's pretty pretty simple. And if I look now at the action space, so all my gym environments have an action space attribute, and I can see that it's a discrete action space of size 2. So because I have 2 actions, left and right. And so all action spaces have a sample attribute, which I can use to sample random actions. So it's just a uniform sampling of the available space. So here, for example, I return the action 1. And should just look at the step function. So now I have taken a random action, and I receive a new observation, which now describes a new state of my system, a new reward. So 1, I still haven't fallen, so I will say the first 1 reward. I still haven't fallen, so my epithet is not done, and the info is empty. So we don't have any more experimental information here. Okay, so now we can do just a quick example. I start by initializing my environment. I will say my first observation, and then until my episode is done, I will simply sample a random action and then step in the environment, and I will look at the sum of the roles that I collect in the environment. So that's pretty simple. And so one thing that can be interesting that I can also visualize the environment. So here, so I take the exact same code, but I simply use my random method here. So I have the random method, so I choose the RGB array, which gives me just a simply NumPy array that I can feed to matplotlib. And I can look at the evolution of the system. So obviously, for now, I'm simply sampling action at random, so I will not last long in my environment. Okay, so I will simply do. So now, so I have my environment all set up. I know how to send actions to my environment, but I not fully picking action in any smart way. I'm simply doing it random. So I will need an agent that can actually learn a policy in the environment. So you see there are plenty of ways to do it. So today I will just introduce stable baseline. So stable baseline is basically a library that gives you access to many implementations of stable and reliable implementation, of deep learning, deep reinforcement learning algorithm. So the last version, which is stable baseline 3, has all implementation in PyTorch. That's the one I will show you today, because before it was in TensorFlow. So I mean, so it's pretty easy, and so it really has a plug and play approach. So I put here the link to the GitHub. It's also completely open source, so you can also contribute. It works on any environment that has a gym interface. That's where like gyms and the standardized API comes really handy, because it just makes the assumption that your environment is a class with the step and reset method and random method. And from now on, it can simply take your environment and feed it to its own training methods. So basically you can do pretty much anything in 2 steps. You simply choose the algorithm that you want to train. So stable baseline comes with, I think now 8 or 10 implementation of really popular, not necessarily state of the art, but popular algorithm that are often used as a baseline in the literature. And so you choose the parameterization of the copy policy or of your value network. So I will go over this quickly. So for example, I will also be showing the example of the proximal policy optimization on our CartPole environment. So, okay. I'm sorry. So I'm trying to I'm not really sure why I don't have Okay, so sorry, just this one. Okay. Okay. Okay, so okay, I will simply go very quickly. I'm sorry, I thought I had organized it differently. Okay, so I'm going back here. And so I will basically what I will do that I will explain it quickly, and then we will do a benchmark, hopefully together, of different algorithms in the environment. And so I will first show you how to use it, and then we will try to understand what's happening. Okay, so in the collab, if you want to do it in the collab, you have all the functions that I'm using, including the evaluate model. But it's actually really straightforward. We just instantiate a model thanks to stable baseline, and this model has a predict method. So as we saw earlier with the agent, it can take takes an observation and returns an action. And so we can take that action, feed it to the environment, receive a reward. And so what we do, we keep doing this until the environment is until the episode is done. And so we do it here for I think for 20 episodes. And this allows us to have an idea of the average performance of an agent in the environment. Okay, so.
Excuse me, Claire, we have a question from Constantine who asks, what is model.predict?
What is model.predict in sense that what it does or how it is implemented?
I think what it does.
Yes, what it does.
Okay, so what it does is that it takes an observation, so which is returned by the environment, and from it returns an action. So basically, it's your policy. So when you have an agent that learns a policy, you want it to be able to look at the state of the environment and gives what the model thinks is the optimal action for that state. And
so it's a kind of model for strategy, right? Model for policy. It's a generator of policy.
Yes,
right?
yes. So exactly. So when you basically instantiate you.
And we need to program ourselves, right? Model predict.
Also, with respect to Jim, yes, you need to program it yourself. But with stable baseline, you basically already have a set of models that are already implemented. So basically, a set of policies that you can directly train. So,
okay.
So you don't really. So if you use stable baseline, you don't have to re-implement. I mean, for the set of base model that exists in stable baseline.
So, for example, if you want to use some approximator like linear function approximator or neural network, it will go in this module or it will go in some other module.
Yes, exactly. Yes.
So exactly what it goes. So if I want to use neural network for strategy generation, it will go inside this model, right?
Yes, exactly.
Okay, thanks.
Maybe can you just show back the slide where you were defining the policy with the MLP initialization? Yeah, this slide, and maybe just the coding line just after where you define your PPO policy, and this one.
Yes. So here, effectively, so I choose a model. So I will maybe spend a little bit of time later if you have any question on this type of model. But basically, what you just need to remember for now is that so this model will be associated with a policy that will learn that will be trained in the environment. And so I'm choosing a type of policy which is simply a fully connected neural network. And I can give it the environment, so it makes all the assumptions that I said about the method available in the Jim environment. And just with these two arguments, I will be able to train the model in stable baseline. So I define here the type of policy that I'm choosing, that I want to learn, and the environment that I want to learn them in. And so that's pretty much it. So is there any other questions or in the chat?
Looks okay.
Okay, so yes, so that's what I can evaluate my model. So obviously now I haven't learned anything. I simply instantiated it. So it was initialized with some random parameters. So it's not doing pretty well. You see that it basically stays for only 9 steps straight and then it just falls. And then I can directly train my agent. So I see that it's really just one line. And so I simply choose that the number of time steps. And so stable baseline will obviously take the policy that I've chosen and update the parameters in function of what it sees when it interacts with the environment. And so after it, now I have a lot of more than 300. So the environment considers full, I think, at starting from approximately 200. So that's
just to make sure.
Oh, it's not random agent.
Yes, just to make sure, we have 100 episodes, and each episode contains 10,000 steps, 10,000 type steps. Am I right?
No. It's basically 10,000 steps is the number of steps that I will train the agent for, and the number of episodes will be determined by how long I simply manage to stay straight. So
but you have something like 10,000 steps on the previous slide.
Yes, so that's basically the total number of steps that I will make in the environment. And when the episode ends, it is automatically reinitialized with the reset function. And so it starts again. So the cat goes back in the middle, and then you start interacting with the environment again until it falls and or reaches, I think, 500 steps. And so the number of episodes at the end will be determined by how long you are able to keep the episode going. I don't know if that's clear.
To say true, I think I'm confused, but well, maybe it's just my problem.
No, but what I think it's basically we will train the agent for 10,000 time steps. And so when
during one episode, right?
Sorry?
During one episode.
I don't know.
In one episode.
No.
In as many episodes as necessary to reach 10,000 time steps.
Okay, so the duration of episodes here is random, and we have a budget of 10,000 time steps, right? And we use this time budget, steps budget to train the model. Am I right?
You have exactly a 10,000 times a budget. The length of the episode is naturally random. It depends on what of the policy you will learn during your training. But yes, but you have a budget of 10,000 times steps.
Okay, not 10. Now it's clear.
Okay, great, perfect. Okay, so now we have a model that seems to work in the sense that we started with something that couldn't last more than 9 steps and it ended up lasting for 300 time steps. So that sounds cool. But we don't really know what happened. So we can use classes called monitors and callbacks and stable baseline to learn a bit more about what's happening during the training, which is obviously very useful if you're actually doing a benchmark for different models. You want to know which model sounds quicker than the other, which one is more stable, etc. So I will show you what you can do with the monitor class. So the monitor is basically what we call a wrapper. So in GIM, which means that when you have an environment with all the meta that we have discussed, you can wrap it in another class, which is also another environment that will inherit all your classical methods, but on which you can add more information on more methods. So that's what the monitor does, and what it does actually is just that every time you take every time you take a step, it simply looks at whether an episode is done or not. And if it's done, it's registered the statistic of the environment, which are your rewards, your total cumulative reward during the episode, and just write it in a file. So I did the same thing, but with the monitor. And so I'm just going a little bit quickly, but because it's probably the same thing. You just wrap it up and you just do model learn. And then you can just look at your logs and you see like the progression of your learning. So it's really, so you can see that it's really, well, it's really noisy. And actually what we're doing right.
Excuse me, what is the x-axis and the y-axis?
So R is the total cumulative reward. And here we have simply the number of episodes.
Okay.
So it's just small question. So it's total reward or total discounted reward?
No, this one is the cumulative reward, not discounted.
Not discounted, but you optimize. That's also, puzzle me somehow that in machine learning community, often people train with respect to one reward, but then display another reward. That always puzzles me, but okay.
Sorry, I didn't really understand. Can you repeat?
So it's a bit strange, to train with respect to one objective and to show another objective. But well, maybe it's the tradition in machine learning.
Yes, well, yes. Well, when you use a discounted reward, you also ensure that you have some convergence properties that you wouldn't have when you're using simply the cumulative reward. But at the end of the day, what you really want in terms of practice is to maximize your cumulative reward. So yes, but so what we're doing now is that we're actually looking at the agent that is looking at an agent that is still learning and actually still exploring in the environment. That's one of the reasons why we have these extremely noisy results, because our agent is learning and exploring at the same time. But when we will use it in practice, it will actually only extract the best policy possible. So to have a better idea of the performance of the agent, we would want to look at what it learns in terms of the best policy possible at every point, at every episode in the process. So we can do this by using a callback. So that's a simple class that we can use in a stable baseline. So I will explain in the notebook, but simply the shape of the callback and the expected method to implement. So in our cases, we will simply set a frequency of evaluation, and every time step, we will simply have a clone of our environment, which will be used purely for evaluation purposes. And we will simply launch our agent with the best policy extracted at that point in our evaluation environment and see what average reward we can collect and write it down in a file. So I'm not go in details in the line. But so yes, so the idea is simply that you can look in the same that you did with the monitor. You can simply look at both your files and print them. So we have here the evaluation of the evaluation. So it's always the total cumulative reward, not discounted. And you can compare it to what you obtain when you're following your still exploring policy. Okay, so that's a nice way to have everything in place to do a benchmark. So I'll took 3 algorithms that of them what we can compare in environment. So the one we looked at just before was proximal policy optimization. So I'm not going in detail about the differences, but basically, when you have your reinforcement learning problem, you can simply say, well, you can say, if we remember the objective, which was to maximize the with the sum of discontinued words, you can look at when you are in a state and you take an action, you will receive a reward. And if you keep following the same policy, you will have an associated discontinued return to the action that you take A in your given state S. So any state action pair can be associated this way with a value that you call a Q value. That's what we've written here. So basically, the first approach is to say we were going to learn this Q value for the best possible policy. Because if we manage to do that, then in any state, we simply have to look at what action is associated with the best value. And we know that this is the value and that's the best possible policy. So that's necessarily the optimal action to take in that state. So that's one approach. So that's what we will do with deep learning. Well, in deep learning, you say, well, to learn that function, I will simply parameterize it by a neural network. So my neural network will try to estimate my execution of my discontinued reward for any action in any state. Or you can try to directly learn your optimal policy, where you say, well, I will simply, well, every time I take an action and I look at my return, I will try to tune a bit my parameters in my policy so that I increase the probability of taking the nice action that led to good rewards, and I decrease the probability of taking the bad action that led to bad rewards. So that's the second approach. And so these three algorithms that I chosen just because they're really popular in the literature and that can be served as good baseline. So we have here the deep learning, which is the first approach, and here we have the two approaches, which are the approach of learning the best policy directly. The only difference is that when you do this, well, when you change your parameters in the policy directly, it can sometimes that's really smooth. You can change your parameters a little bit and have a huge change in the action that you're taking. So in this last algorithm, we try to say, okay, we're actually only moving on the safe zone around the policy that we know works maybe okay, so that we don't end up with an extremely bad policy. So that's basically the algorithm that we can compare. And so once we have this, you can see that so all of them are already implemented in stable baselines. So you can just simply import the three classes. And so here you have an example of a really basically short benchmark when you simply can define your model, and you can simply here train every single of them and register that performance, the evaluation of our performance in training and evaluation during 20,006. So I don't know if you want to.
Just a small question. What is learning? Yes, on the previous slide, it was learning stats or something like this.
Learning. Oh yeah. So actually, I didn't end up. Oh, okay. Oh, I use it. Yes. So learning start just means that you're going to start learning after collecting 500. So here 500 transitions. So after visiting 500 states in the environment.
So you visit this 500 randomly, or you visit with the learned policy?
With your policy, but that is not learned. But with your policy, but you haven't learned anything yet, so it's almost random.
Okay, so it's just pure exploration. You can say that we can say that it's just pure exploration stage, right?
Yes.
Okay.
Into exploration. So I don't know which one you prefer. We can either try to do the benchmark together, or we can code an environment. I don't know which one you will do.
Me, I vote for coding an environment.
Okay, let's do.
I'm an opinion leader.
Okay.
Otherwise, just summary that deep learning phase of work, like I did correct.
Well, you can, well, in this benchmark, it's the worst performing, but it's also because I didn't do any tuning of hyperparameters, so I can't really conclude much. But
If you don't want to tune, don't use it.
If you don't want to choose the weights of the neural network one by hand.
So you can either choose any problem that you would like to turn into reinforcement learning problem and try to see what you can get from it. I also propose on the club, if you have it, a simple game, which basically is so if you have an agent and the agent should go toward that goal here in green, and that's a cliff, doesn't look like it, but it's a cliff. So if the agent ever goes in the black, he dies. So I don't know, we can maybe try to look at how we could code this, or if you have any other idea of an environment you would like to.
It's still a single agent.
Yes, it's a single agent. Yeah. I only did single agent.
And I have a question about this stable baseline. Right?
Yeah.
How well do they perform on which kind of problem can you solve with them? I get that they solve like the CartPole problem, for instance.
Yeah.
But let's say that I have a problem in a completely different domain and I code the environment. Do I have a chance that some of the stable baseline they find a reasonable solution to the problem, or most likely I will need to do tuning or code my own?
So most likely you have to do tuning and code your own. So what this can give you is that you will have a first baseline, and also you can work on it. So you can start from what they provide and work on it.
Okay.
But yeah, so if you have, maybe I'm going to be a bit less pessimistic. If you have a simple problem, if you have, like, for example, a discrete action space with a reasonable size, so, for example, so you can hope for simple, basically just to, in stable baseline, you have, I think, 8 or 10 different algorithms. So it's more, the stable baseline basically brings everything you have in terms of tuning, in terms of little tricks that you can imagine to make this algorithm work. So in terms of what this algorithm can do without any addition, it's pretty much the best that you can find. But these algorithms are limited because they always, well, they have mostly been tested on classic benchmarks that you see in GIM. Yeah,
They don't make any assumptions.
Yeah. So yes, if you have a specific problem that's not a standard classic control learning task or a simple agent that you're trying to make work, you probably will have to tune it.
For instance, does it work on your example?
On my example, well, I'm a bit frustrated. Let's do it. So yeah, I'm a bit frustrated because I managed to make it half work, but I did that. I lacked time to see if I could tune it because I didn't do much tuning. I didn't have much time, so I didn't know if I could make it work better if I had more time to tune it. I'm a bit frustrated for that.
But just excuse me. So in your example, so time is discrete, I guess.
Yeah.
And so you have an agent which is a circle or something like that.
Yeah.
And the allowed moves are just 1 pixel up. What are the rules exactly?
So I decided that the allowed move would be an action of 2 with a dx and a dy, with a dx and dy. Okay. So I can basically move a little bit like that, a little bit like that. And so
with some limit on the
with some limit, yes, it's within -1 and 1.
Okay, so you have the 8 possible moves of the king.
Yes, but I do it in continuous mode, so I can choose between 0 and 1.
Okay.
Between -1 and 1. Okay. I wanted to try with the continuous space. I think it probably would have been easier with a discrete space. I wanted to do what I could manage to do with a continuous space. So yes, so I have a limited update with a bit rectangle of -1.
And excuse me, from the point of view of the agent, the state space is what exactly?
It's the position.
Is only the position.
Yes, only.
Okay, but you always
Always the
have
same,
the
yeah.
same landscape
Yeah,
in
exactly,
terms
the
of
same landscape.
where the cliff is and so on.
Yes.
And sorry, the question, but so it gives you an observation, and you said that you don't necessarily observe the true state, right? So do you have, for this kind of problem, do you have a way also to know what is the true state? Like if it's on the grid, for example, and you don't really observe the true position, I mean, to benchmark your algorithm.
Yeah, so basically that's an assumption that you're going to make when you're going to choose an algorithm. You're going to say, okay, so I'm not observing the full state of my environment. So maybe I'm going to keep track of maybe, I don't know, some condition probabilities between the different observations to see if I can try to estimate better the underlying state of the environment. So for now, the unstable baseline, they haven't implemented this. For now, it's only they just assume that you have the full state. But yes.
But in fact, you can implement a partially observable NDP as a gym environment.
Yeah.
And you can always try to use your favorite stable baseline algorithm and see what happens.
Yes. And sometimes it works. Not often, but sometimes.
Yeah, I mean, I know
you don't seem convinced.
Exact algorithm for UMDPs are very complex. I mean, they don't assume the state.
Well, the exact one, yes.
But maybe in this framework, you can get it.
So yes, so obviously there are many different ways to implement it. So what I did is that I tried to do box of I take -1 measure. Yeah, I need to choose. And so I just have an observation state, which is just my position in the environment, and I can take some actions when I choose. Should be one here, but so I can go up and down. And so to the step. So what I did is that I simply, so I take the action that should give me my déplacement, my move. Thank you. So along my X and Y axis, and okay, so that's simply an outdated version. Well, it works, but that's an outdated version where I did direction and the velocity. So that's a little bit different, but that's the same principle. It means that you translate it into your move on the X and Y. And so once you have this, you will send just a copy of your new position. So that's your new observation that you give back to the agent. But you also need to give back a reward to tell if the episode is done or not, and to give eventually supplementary info. We don't really need to do this. So one way to do it is to use your knowledge of the position of an agent to see how far away it is from the goal. And you say, well, maybe the distance is less than a completely the distance that you choose. You consider that the agent has reached the goal, and then you say, okay, now you can stop, and you will give him a good feedback. So here I choose 100. You can do the same thing for the cliff and give back a boundary roll. So the main idea is that you shouldn't set up an environment in which it is more advantageous for your agent to simply die on the cliff. Because I mean, if the agent, if it stays extremely long in the environment and never falls in the cliff, but always gathers a reward that is negative because it hasn't reached the agent, can end up actually find out that the best strategy is to simply die immediately, which is not what we want. that's one of the things that you have to think about when you design your reward function, because you essentially has to map to your problem. Okay, and so yeah, so what I did is that I simply give a reward when he's not later at the cliff, reward which is a function of a distance towards the goal. Obviously, there is a bit of a trap here, because you can't really, well, ideally, which is why I'm a bit frustrated, but I haven't really spent enough time on it maybe. Ideally, the agent, no matter where you would put it, he will learn to go around the cliff, because obviously if it only follows the reward function, it will fall on the cliff, because you can simply, if the cliff is value, you could simply cross it on the horizontal.
In fact, yes, and also in designing the reward function in this way, in some sense, you put some of your human understanding of the problem into the system, which is a bit annoying, because, for example, if you take, I don't know, very complicated abstract game like chess or Go or Gomoku or Mahjong or whatever, maybe you don't have such a good evaluation function yourself, and you just have the final reward of the game, which is you lost or you won. And so it's a bit disturbing to have to use this kind of trick.
Well, I think the general idea in reinforcement learning in general is that we ideally would tend toward the situation where we wouldn't need to do this. And so sometimes in some games, actually, it's actually possible to just take a screenshot now of the game and to just use the result of the episode in the game as a reward function. And it works on some simple games, but especially in anything that's about industrial application, that's not really, that haven't really worked for now. So you generally, when you do this kind of, now it's really just a simple game, and when you have to work on a practical application, you try to put as much of your human knowledge in it.
Yeah, sure.
But yes.
But it's very disturbing to see that even in a very, very simple environment, in fact, which should be an easy one, I had exactly the same problem when I played around with Jim and stable baseline. So it's not a criticism of what you do, quite the contrary.
Would you find some kind of reasonable policy if the reward was binary, like just off the cliff or not?
Well, I tried to do it. I didn't manage to make it out. But again, I don't want to conclude too much of it, because I really use the simple classes. I didn't do any fine tuning. I'm using really simple base algorithm, so I don't want to conclude much from it. But so yeah, I think when you look at the literature, it seems that you have some algorithm with some kind of fine tuning also that managed to work pretty well with me, even very sparse reward. So I had worked on some algorithm where you basically have no reward for much of the episode in the game, because you need to actually open a door and find the key and put the key, etc. And it takes a lot of time. So then you have to wait until 1 million, 10 million, 100 million time step in the environment. That was also one problem. But then you manage to make it work, provided that you have a good exploration policy and strategy, etc. So yes, possible. So I don't know if so yeah, that's one way I try to do it. So there are many different ways. So I try to instantiate my environment this way. I use a really simple SAC algorithm. So SAC is also a version of the second option, so the actor critique option, where you try to directly optimize the policy. I said in SAC, you try to push the policy to always keeping its option open. So you always try to to maintain a level and entropy on the action that the policy can choose. And so the last thing that can be useful is that you can register your environment. And so you do it very simply with the gym.env register. You choose an ID. You simply point to where your class is, and you can set up a number of max of maximum steps in the environment. Okay, and then so I've been trying to train my my model. So that's one of the training that I managed to do. So I managed to have a reward of 61, which means that it has finally reached the goal. But you will see that I have cheated. So basically, yes, I wanted to be able to do it in the workshop, but so I tried to limit myself to something that could be learned quickly. So I tried to. So I thought, okay, I was like, wait, it works, and then I didn't have much time to see if I could pass it back here. So, but now I'm very. I mean, I don't know. I'm trying to. I think I will maybe spend a little time on it again to see if I can manage to make it work starting here. So that's pretty much it. So we didn't really have the time to do coding together. Maybe I spoken too much.
No, don't worry. But as a matter of fact, yeah, it's the end of the hour, so I think we can go for a round of applause for Claire.